Okay, let's talk about data representation from Chapter 1 a little bit. First of all, we'll talk about what a number is and a numeral is, just to get those separate, and then we'll move on to things like binary and hex and all that good stuff. So first of all, a number is just a sort of an abstract thing that we use to represent quantity or measurement of some sort. So I've got 6 squiggles that maybe look like apples, maybe don't, but there's 6 of them there regardless. Okay? We have different ways of representing those when we write them down, and those are using numerals. So we would use something like this to represent that amount. That's 6. But that's not the only way to write them. There might be a Roman numeral system like that. There could also be a binary representation like that, or even a unary representation like that. So those are all numbers, or numerals rather, that represent the same number 6. And so what we're going to be interested in is describing different number systems, numerals, that we can use to represent quantities, and in particular, ones that we use in a computer. And that would be binary and hex. So let's start out with a number written in decimal, 465. This is using base 10 in our Arabic numeral system that we use today to write numbers down. And I put a little 10 subscript there just to make sure that this is a base 10 number. Since we're dealing with all different kinds of numbers, it will help us later on to have that subscript there. All right? So 465. We all know what that means. Well, we should go ahead and review the idea of a place value system, because that will help us when we start to think about binary, which is what we want to do next. So what we do is every place from right to left is associated with the power of the base that we're using. So since it's base 10, this represents 10 to the 0, the ones place. This represents 10 to the first, the tens place. And this represents 10 to the second, or the hundreds place. Okay? So we could expand this number out and write it like this. 4 times 10 squared plus 6 times 10 to the first plus 5 times 10 to the 0. Okay? Or 4 times 100 plus 6 times 10 plus 5 times 1, because anything raised to the 0th power is 1, or 400 plus 60 plus 5, which gives us our original number, 465. Luckily for us, binary works just the same way. It's the only thing really different is that we have a smaller number of numbers, digits to choose from, and we change the base from 10 to 2. Okay, let's take a look at a different number represented in a different numeral system. This is a number in base 2, or binary. So every digit that we use can only be 2 choices, either a 0 or a 1. Okay, in decimal we have 10 choices because it's base 10, 0 through 9. In binary we have 2 choices because it's base 2, 0 or 1. Okay? But the place system idea works exactly the same. So this is our times 10, or 2 to the 0, times 2 to the first, 2 squared, cubed, to the 4th, to the 5th. Okay? So each place represents a power of the base, which is 2. And so we could convert this number to decimal, just like we did with our place value example on 465 just a second ago. All right? So this would be 1 times 2 to the 5th plus And I'm just going to skip the ones that are 0 because 0 times anything is 0. So skip that, and then go to the next one. And I've got 1 times 2 squared. Skip that. The last one, 1 times 2 to the 0 power. All right, so that's 1 times 32 plus 1 times 4 plus 1 times 1, or 32 plus 4 plus 1, or 37. So this number in binary is 37 in decimal. All right, so that explains the place value system for binary numbers. It also shows you how to convert from binary to decimal. All right, now what if I want to go the other way? What if I want to convert from decimal to binary? Okay? This one's a little bit more difficult because instead of knowing powers of 2, I need to know how to divide by 2 and then determine whether there's a remainder or not. All right? So 465 base 10, our decimal number. We're going to convert that into binary. So what we need to do is divide that by 2. And what do we get? We track not only the result of the division, but the remainder after division. So it turns out that that is 232, remainder 1. Okay? So our 1 basically now means that this original number was odd, and it would be our rightmost bit in the binary number. And then divide this by 2. Keep going until this gets to 0. Okay? So this would be 116, remainder 0, which means that the next bit from right to left is a 0. This divided by 2 is 58, remainder 0. So the 0 is the next one up there. Okay? Dividing this by 2 gives me 29, remainder 0. So I have yet another 0 in my binary number that I'm forming. Okay, I'm going to move up over here so that we can stay on camera. 29 divided by 2 is 14, remainder 1. And so I have a 1 there. Divide the 14 by 2, 7, remainder 0. Next bit is a 0. Divide the 7 by 2, 3, remainder 1. Goes there. And divide the 3 by 2, 1, remainder 1. And finally divide the 1 by 2, and I get 0, remainder 1. And that's what tells me that I'm done with the process. This is my last bit that goes up there. Okay? So 1, 1, 1, 0, 1, 0, 0, 0, 1 is the binary equivalent of 465. Now what's going to get you in this process is if you list the bits backwards. In other words, if I start with this as the leftmost bit and then go to the right with my remainders, instead of starting at the right and going to the left, you're going to get entirely the wrong number because it would be backwards. Okay? So just remember, when you're doing the bits, they go that way, right to left. Okay, now let's talk about hexadecimal, or hex, which is base 16. So now each place in the numbers that we end up representing, the numerals that we end up writing, will be a power of 16, or multiple of a power of 16. Just like we had multiples of powers of 10 with decimal, multiples of powers of 2 with binary. All right? So, since it's base 16, each place has to have 16 possible choices for its value. In decimal, we have 10 possible choices, 0 through 9. In binary, we have 2 possible choices, 0 or 1. So we have to have 16 possible choices, 0 through 15, in hex. So, the way that we do hex is like this. It's represented, first of all, 0 through 9 are just 0 through 9 in our decimal system. So that's where it sort of becomes important to know what base you're working with, because it matters. But now we need a different symbol to represent 10, a 10th digit, if you will. So what we've agreed to do as a community is do letters, generally capital letters. So A, B, C, D, E, and F represent 10 through 15. Okay? So there's our hex digits, the things that will be in our place value system when we're writing hex. It's also going to be handy to have the bit patterns that are associated with these. So what I'll do is write out 4 bits that are the binary equivalent of these numbers. So that's just 4 bits to say 0, obviously. I don't need all 4, but it's handy to have it that way, and you'll see why later. Then 1, 2, 3, and so on. There's my first half of the table with the bit patterns, and I can fill in the rest. Made a mistake there, didn't I? That's a 0. 0, 1. There we go. Alright, so there are bit patterns associated with all 16 of the possible hex digits. That table's in the book, and you're going to need it. It'll come in handy when you're doing things like converting binary to hex or hex to binary, and we'll show you that later. Okay, now here's a hexadecimal numeral representing some number, and what I want to do is translate it into decimal. It's a place value system, just like decimal and binary were. So each place represents a power, but not of 2 or 10 for binary decimal, but 16 because we're working in hex. So this number, or numeral, this representation, if I want to convert it into decimal, goes like this. A, and we'll talk about what that is in a minute, times 16 squared plus 9 times 16 to the first plus e times 16 to the 0 power. All right, remember that we had different values for these. These represent different numbers. So this is 10 times 256. So the 10 is the decimal equivalent of this hex digit. 16 squared is 256. Plus 9 times 16. That's pretty self-explanatory. And then this one is 14 times 1, because E represented 14. All right? So 2,560 plus 144 plus 14, if I do the math, and add all that together, and I end up with 2718 in base 10. So this number in hexadecimal representation looks like that, and in decimal looks like that. It's the same process, it's just using different bases and different digits. The concept, though, is the same. All right, now let's go over how we would convert a decimal number, 787, into hex. When we did decimal to binary, we divided by 2 multiple times. We'll do the same thing here. So I'm going to take this number and I'm dividing by the base. The base in hexadecimal, where I want to go, is 16. So this divided by 16 turns out to be 49 with a remainder of 3. All right, so my first digit in the hex equivalent is 3. Divide that by 16 again, and that would be 3 with a remainder of 1. 16 times 3 is 48. So 1 is the next digit in my hexadecimal representation. And then last but not least, if I divide this by 16, it's 0 with a remainder of 3. And so 3 up there finishes off my representation in hex. So 787 in decimal is equivalent to 300. Okay, so one of the nice things about hexadecimal is that converting from hex to binary or binary to hex is really easy, and that's why a lot of times we represent long binary numbers as shorter looking hexadecimal numbers. It makes for an easy conversion. So let's see how to convert this hexadecimal value into binary. Basically all you have to do is go and look up the bit patterns from the table that we had drawn up here before and stick them together. So an F is represented by 4 ones, and a 3 is 0, 0, 1, 1. Then our A is 1, 0, 1, 0. And finally our 9, 1, 0, 0, 1. And so there is the representation of this number in binary. It's just taking each of the bit patterns from the table, sticking them together, end to end like that. Simple. Okay, our last piece here. How do we turn a binary representation into hex? It's the reverse of the process we just talked about. You would look up these groups of 4 bits in the table and write down the corresponding hex digit. Simple, right? So I've written this number, which is 16 bits long, in a little bit of a odd fashion that I broke up the 4-bit groupings to make it easier. All right, so whenever you're looking at this, you have to look at in groups of 4. Well, 1011 is a B in the table. 1011 is also a B. 1110 was an E in the table. And last but not least, 0001 in the table is a 1. And so this value in binary is equal to this value in hex, BBE1. Okay? So you can convert between all these different types of bases by either dividing or multiplying according to the base of the system that you're using, whether it be 2, 10, or 16. We use decimal in the real world, computers use binary, and then we have hex as a way of shortening up the binary.